Assalamualaikum and hi to everyone. In this video, I will explain two questions related to bot plot analysis and transfer function, which are important topics in control system engineering. The first question requires us to construct the bot magnitude plot from given transfer function. To solve this problem, I first convert the transfer function into its standard bot form. This allows me to identify the system gain, zeros and poles more easily. From the equation, I found that the system contains the first one 0 at the origin and one pole at 5 rate second, and the last one double pole at 20 rate seconds. After determining the gain value, I analyzed how each pole and zero affect the slope of the bot plot. A zero contributes plus 20 dB per decade, while each pole contributes negative 20 dB per decade. By combining this effect, I can determine the overall shape of the bot magnitude plot. So, the second question is the reverse process. Instead of being given a transfer function, we are given a bot plot and need to determine the transfer function of the system. To do this, I examine the changes in slope throughout the graph. Every increase in the slope indicates the presence of a zero, while every decrease indicates the presence of a pole. By identifying the break frequencies and the slope changes, I can determine the location of the pole and zeros and then reconstruct the transfer function. So, in conclusions, these two equations demonstrate the relationship between transfer function and the bot plots. The first equation shows how to obtain a bot plot from a transfer function, while the second one shows how to derive a transfer function from a bot plot. So both techniques are essential for analyzing the frequencies response and stability of control system. So that's all from me. Thank you.
Hello everyone, my name is Enol Brian Anak Arismo, and today I'm going to explain about our transfer function. And this is the question that we got. We got transfer function A. So the question is h omega is equal to 300 j omega over j omega plus 5 times j omega plus 20 square. So first, we have to change it to the standard bot plot form. So for uh, j omega plus 5, we have to factor out the 5. Same goes to the 20. J omega plus 20 square, we have to factor out the number which is 20. So and then we substitute into the formula, and we have to multiply 5 with 20 square, and we got 2000. So we have to simplify the equation, that is 300 divided by 2000. So we got the final answer is 0.15 j omega over 1 plus j omega over 5 times 1 plus j omega over 20 square. So this is the final equation that we got for the standard bot plot form. So 0.15 is for the k, that is gain. J omega is for the zero at the origin. 1 plus j omega over 5, the simple pole. And then 1 plus j omega over 20 square is a double pole. Because we identify the n is power of 2. That's why it is double pole. Okay, moving on. Next, I will explain the magnitude bot plot analysis. First, we need to find the value of constant gain, which is k. From the standard form, k is calculated by using k is equal to 300 over 5 times 20 square. Here, the value 300 comes from the numerator of the transfer function, and the value 5 and 20 comes from the denominator after we convert it into standard bot form. Okay, next, after we calculate all of this, we get k is equal to 0.15. After finding k, we convert it into decimal form using this formula. That is 20 log 10 k. where we got from this equation, that is factor k, the magnitude, the equation is 20 log 10 and then k. So we just substitute 0.15 and then we get negative 16.47 dB. This value is the starting magnitude level for the Belk plot. So in simple words, this shows how we can find the initial gain of the magnitude Belk plot, which start around negative 16.47 dB. Now, I'm going to explain the slope change for the magnitude Belk plot. In Belk plot, every zero and pole will affect the slope of the graph. For this transfer function, we have three important parts. First is zero at origin, second is simple pole at omega is equal to 5, and third is double pole at omega is equal to 20. So first, we look at the zero at origin. As we can see from the transfer function formula, it is written as j omega power of n, where the n is equal to 1. So, for a zero at origin, the slope is positive 20 dB. Since 20 and the n is equal to 1, so 20 times 1 is equal to positive 20 dB. This means the graph will increase with a slope of positive 20 dB. So next, I'm going to explain about simple pole at omega is equal to 5. We have a pole at omega is equal to 5. This comes from 1 over 1 plus j omega over 5, this equation. So this a simple pole give a slope negative 20 dB based on the equation given. The screenshot that above and the below slope change. So after the pole at omega is 5, the slope become negative 20 because before the point, the slope was positive 20. So after the pole equal to omega 5, we have to calculate after pole there is positive 20 minus 20. So that's why the graph become flat because the final answer is 0 dB. And next, we have to calculate the flat level at omega is equal to 5. So how do we do that? We use the equation for gain. That is h omega is equal to 20 log k. So first, what we're gonna do, we just substitute the equation for k and also omega. So hash 5 is equal to 20 log 0.5 plus 20 log 5. And then we combine inside the log 0.15 times 5 is equal to 0.75. So the final answer is negative 2.5 dB. So the flat level is approximately negative 2.5 dB. This means from omega 5 to omega 20, the graph is flat around negative 2.5 dB. Okay, now I'm going to continue with the slope change after omega is equal to 20 radian. Before this point, the slope from omega is equal to 5 to omega equal to 20 is already flat, which is 0 dB. This happens because the zero at origin give positive 20 dB and the simple pole at omega 5 give negative 20. So positive 20 minus 20 is equal to 0 dB. That's why it is flat before the pole. And after the double pole at omega is equal to 20, we get the equation here is 1 over open bracket 1 plus j omega over 20 close bracket square. Because the power is 2, this is called double pole. A normal simple pole gives negative 20 dB, but because this is a double pole, we multiply it by 2. So negative 20 times 2 is equal to negative 40. So the double pole gives a slope change of negative 40 dB. So before omega is equal to 20, the slope was 0 dB. But after the double pole, the slope becomes negative 40 because 0 minus 40 is equal to negative 40. The 0 is we take when omega equal to 5 until 20. That is the flat line. That's why it is 0. So after omega is equal to 20, the magnitude dot plot start decreasing with a slope of negative 40. That is why the small graph at the bottom shows a downward line, and the downward line represents the effect of a pole. So next, I'm going to explain about the table. The table on the right summarizes all the frequency range. For the first range, omega until 5 radian, it is 0 at origin, so the slope is positive 20 dB. And for the second range, from 5 until 20, we take the before slope minus the current slope, the simple pole slope. So the simple pole slope give negative 20. So we put it into calculation, that is before minus after, we get 0. Positive 20 minus 20. So it is 0 dB. That means the graph is flat in range of 5 until 20. And then for the third range, that is omega until 20, the previous slope is already 0. And the double pole gives negative 40. So 0 minus 40 is equal to negative 40 dB. That means the graph decreases after omega is equal to 20. Alright, that's all for the slope change. Before I continue with the final bar plot, I use this bar plot reference table as a guide. This table shows the basic shape for magnitude and phase plot for different factors in the transfer function. For my calculation, I mainly focus on the magnitude plot part. First, for the constant gain k, the reference table shows that the magnitude is 20 log 10 k. This is why earlier I calculated 20 log 10 open bracket 0.15 close bracket is equal to negative 16.47 dB. So this value become the starting magnitude level. Next, the table shows the factor, that is open bracket j omega close bracket and power of n. This represent a 0 at origin. From the reference table, a 0 at origin gives a positive slope, that is positive 20 n dB. And in this case, our n is equal to 1, so the slope is positive 20 dB. That is why the both plots start by going upward. Then, the table shows the pole factor, that is 1 over open bracket 1 plus j omega over p close bracket and the power of n. This is represent a pole. A simple pole gives a negative 20 dB. For my transfer function, the first pole is at omega is equal to 5. So omega is equal to 5. The slope changes from positive 20 minus 20 and it equal to 0 dB. This is why the graph becomes flat. For the second pole, my transfer function has 1 over open bracket 1 plus j omega over 20 close bracket and then the power of 2. Because the power is 2, this is a double pole. Using this reference table, one pole gives negative 20 dB, so double pole gives negative 20 times 2 is equal to negative 40 dB. This is why after omega is equal to 20, the graph will decrease with slope negative 40 dB. So basically, this reference table helps me identify the effect of each factor in the transfer function. The gain gives me the starting level, the 0 at origin gives a positive slope, the simple pole reduced by the slope by 20, and the double pole reduced the slope by 40. That is why how I know the final shape of my magnitude bar plot. Thank you.
Good day everyone, today I will be representing the both magnitude plot of our system as illustrated on this graph. To give you an overview, this system consists of our individual component, a constant gain, a zero origin, a simple pole and a double pole. Together, these elements define the system overall transfer function. First, Let's look at the horizontal blue line label 1. They represent our constant gain factor, calculated as 20 log 0.15, which set as at approximately minus 60.5 dB. This component provides a flat baseline offset for the entire plot. Next, the straight sloping line label 2 represents a 0 at the origin, given by 20 log j omega. This line passes exactly through 0 dB at the frequency omega equal to 1 radian per second and maintains a constant upward slope of positive 20 dB over decade. Moving on, the line label 3 is a simple pole with a break frequency at omega equal to 5 radian per second. Notice that its magnitude remains flat at 0 dB until it hits 5 radian per second, after which it begins to slope downward at rate of minus 20 dB over decade. Finally, component number 4 represents a double pole with a break frequency at omega equal to 20 radian per second. Because it is a second order pole, it stays at 0 dB until omega equal to 20 and they drop sharply at a much steeper rate of minus 40 dB over decade. Now let's look at how the final composite result represented by the solid red line is constructed by graphically adding all these components together across different frequency range. For frequencies below 5 radian per second, the only active slope comes from the 0 at the origin, positive 20 dB over decade. Combined with our constant gain, the red line climbs steadily at positive 20 dB over decade, starting from minus 36.5 dB omega equal to 0.1 and peaking exactly at 0 dB when it reached omega equal to 5 between 5 radian second and 20 radian seconds. Once the frequency past 5 steps, the simple pole active with a slope of minus 20 steps over decade. This completely cancel out the positive 20 dB over decade slope from the 0. As a result, the net slope becomes 0 dB over decade, creating a flat plateau at 0 dB for frequency above 20 radian over second. As soon as we cross the final corner frequency of 20 radian per second, the double pole kicks in with a slope of minus 40 dB over decade. Add to the previous flat response, the final red line plunges downward at a total net slope of minus 40 dB over decade. In conclusion, the final red curve clearly outlines the magnitude response of the system. It effectively acts like a band pass filter, alternating both very low and very high frequency while maintaining a stable flat 0 dB gain response between 5 radian per second and 20 radian per second. Thank you. Moving on the both phase plot as shown in the graph, we can see how the total phase angle response shift across the frequency spectrum based on our phasor equation. In our mathematical derivation, the constant gain factor contributes a baseline phase angle of exactly 0 degree across all frequencies, while the simple 0 at the origin contributes a constant phase shift of 90 degree for all frequencies, which is shown by the solid horizontal line at 90 degree on the left side of the graph. The first order simple pole at omega equal to 5 radian per second begins dropping at phase 1 decade before the corner frequency at omega equal to 0.5 radian per second and settle at minus 90 degree 1 decade after at omega equal to 15 radian per second with a downward slope of minus 45 degree per decade. Meanwhile, the second order double pole at omega equal to 20 radian per second drops twice as fast, starting its decline at omega equal to 2 radian per second and finishing at omega equal to 200 radian per second, with a step downward slope of minus 90 degree to eventually contribute a total phase shift of minus 118 degree. By accumulating these individual straight line approximation slope together from left to right, we get the final solid rate phase plot line. For frequency below 0.5 radian per second, where no poles have activated yet, the phase stays perfectly flat at 90 degree due to the zero at the origin. From 0.5 radian per second to 2 radian per second, the first pole activates and changes the net slope to minus 45 degree, bringing the red line down from 19 degree to 45 degree exactly at omega 2 radian per second. Between 2 radian per second and 50 radian per second, the double pole also become active, combining with our first slope to create a very steep net slope of minus 135 degree, where the red line across 0 degree and flattens our slightly once the first pole finish its drop at omega equal to 15 radian per second. From 15 radian per second to 200 radian per second, only the double pole is left looping, so the net slope reduced back to minus 16 degree until the double pole reach the final value at omega equal to 200 radian per second. Beyond 200 radian per second, all phase variation are complete, and this total final phase angle of system level out asymptotically at minus 118 degree. That's all. Thank you.
Assalamualaikum and hi. My name is Ahmad Tamal Nizam. In this video, I will explain how to analyze the Bode magnitude plot before finding the transfer function. First, let's observe the graph carefully. The vertical axis represents the magnitude in the decibel or dB, while the horizontal axis represents the logarithm of angular frequency, which is log omega. The graph starts at 40 dB and has a slope of negative 20 dB per decade. A slope of negative 20 dB per decade is indicate that the system contains one pole at the origin. This means the transfer function has 1 over s, or in frequency domain 1 over j omega. Next, at omega equal to 1, the slope change from negative 20 dB per decade to 0 dB per decade. The slope increase by positive 20 dB per decade. Whenever the slope increase by 20 dB per decade, it means 0 is added. Therefore, the first 0 is located at omega equal 1. After that, between omega equal 1 and omega equal 2, the graph becomes horizontal. A horizontal line means the slope is 0 dB per decade, showing that the added 0 has cancelled the effect of the pole. Next, at omega equal to 2, the slope changes from 0 to positive 20 dB per decade. Again, the slope increased by 20 dB per decade, so another 0 is added. This given us the second 0 at omega equal 2. Finally, at omega equal 3, the slope changes from positive 20 dB per decade to negative 40 dB per decade. The total change is positive 20 minus negative 40 equal negative 60 dB per decade. A change of negative 60 dB per decade means 3 poles are added at the same rate frequency. Therefore, there are 3 coincident poles at omega equal 3. So, from the Bode plot, we have identified 1 pole at the origin, 1 0 at the omega equal 1, and 1 0 at omega equal 2, and 3 pole at omega equal 3. These are the important characteristics that we will use to construct the transfer function in the next video. Now, I will derive the transfer function based on the information obtained from the both plot. First, we start with the standard transfer function. The general form is h of s equal k multiplied by all zero term divided by all whole term. Since we identified one pole at the origin, the denominator contains s. The first zero is at omega equal 1, so its factor become 1 plus s over 1. The second zero is at omega equal 2. Therefore, its factor is 2 plus s over 2. Finally, we have 3 poles located at omega equal 3. Since all 3 poles occur at the same frequency, the denominator become 1 plus s over 3 raised to the power of 3. Combining everything together, the transfer function become h of s equal k multiplied by 1 plus s over 1 times 1 plus s over 2 divided by s times 1 plus s over 3 raised to the power of 3. The next step is determining the value of k. From the graph, the starting magnitude is 40 dB. Using the gain formula, 20 log 10k equal 40. Dividing both sides by 20 give log 10k equal 2. Taking the algorithm, k equal 10 squared, which is equal to 100. Therefore, the gain content is k equal 100. In the next video, I will substitute this value into the transfer function and write the final expression in the frequency domain. Okay. Now, I will complete the final transfer function. Since the gain content constant is equal to 100, I substitute it into the equation. The transfer function in the S domain becomes h of s equal 100 times 1 plus s over 1 times 1 plus s over 2 divided by s times 1 plus s over 3 raised to the power of 3. Because the both plot represent frequency response, we replace the variable s with j omega. This gives the frequency response as h of j omega equal 100 times 1 plus j omega over 1 times 1 plus j omega over 2 divided by j omega times 1 plus j omega over 3 raised to the power of 3. This is the final transfer function obtained directly from the both magnitude plot. To summarize, the important steps are: first, identify every change in slope. Second, determine whether each change represents a zero or a pole. Third, write the transfer function using the standard form. Finally, calculate the gain constant k from the initial magnitude and substitute it into the equation. That complete the solution for this question. That's all from me. Thank you.
Assalamualaikum to everyone. Today, I would like to discuss the result obtained question A. First of all, based on the transfer function and the both plots obtained, the results are consistent with the theoretical characteristics of the system. The change in magnitude slope and phase angle on Q at the expected break frequencies, which are at the 5 radian per second and 20 radian per second. The percent of 1 0 at the origin, one pole at 5 radian per second and a double pole at 20 radian per second determine the overall frequency response of the system. This pole and zero produce the expected charge in the magnitude and phase plot. Therefore, the obtained both plot accurately represent the behavior of the transfer function. These show the manual calculation and the plot graph agree with the theoretical both plot analysis. For conclusion, for discussion question A, the result obtained are valid and meet the expected frequency response of the given transfer function. Thank you. Assalamualaikum. Welcome back to me.
Now I want to talk about discussion for question E. Okay, based on the given both magnitude plot, the transfer function can be obtained by identifying the gain, pose and zero from the slope change. The graph starts with a slope of negative 20 dB per decade, indicating the presence of one plot at the origin. At 1 radian per second, the slope increased by 20 dB per decade, which indicates the first zero. At 2 radians per second, another increase of 20 dB per decade indicates the second zero. Finally, at 3 radian per second, the slope decreased by 60 dB per decade, showing that there are 3 poles and that break frequency. From the graph, the gain in 40 dB, therefore the value of k is 100. Based on all the observation, the transfer function obtained is h open bracket j omega close bracket equal to 100 open bracket 1 plus j omega per 1 close bracket, and then open bracket again 1 plus j omega per 2 close bracket equal to j omega open bracket 1 plus j omega per 3 close bracket power of 3. In conclusion of discussion question E, the transfer function obtained is consistent with the characteristic of the given both plot, where every change in slope corresponds to the location of the plot and zero. Thank you. Okay, now we already talked about question number A and question number E discussion. Now we want to talk about conclusion for this assignment. For this assignment has demonstrated how both plot analysis can be used to study the frequency response of a system. For question A, the given transfer function was successfully converted into magnitude and phase both plots. And for question number E, the transfer function was successfully determined from the given magnitude both plot by identifying the gain, pose and zero. Overall, the result obtained are consistent with the theoretical both plot analysis.